Welcome back, folks. This is lecture number 9. Before we get started, I wanted to do a quick review of the current divider. I wanted to then introduce something called mesh analysis, and then we will continue on with our introduction to AC circuits. We are given this circuit. You're asked to find the current through resistor R4. So that's I of R4. There's two general ways you could approach this problem. You could determine the voltage across R4 and then use Ohm's law. You could also determine the current that's applied here and then use the current divider rule. To get us started, consider this. What is the current here? Or what is the current here? I think you'll agree that this current meter, and this current meter all read the same thing because that part of the circuit is in series. However, these two current meters will read different because they are in parallel, right? R3 and R4 are in parallel. But the sum of these two, right? The sum of those two meters would equal any of the others that we've drawn. We can fairly easily calculate the current through this meter. We would just have to figure out what the total resistance of this circuit is and then use Ohm's law. So let's give that a try. So the total resistance of this circuit is 10 plus 2 plus 5 in parallel with 10. Run that through the calculator real quick. We would say 5 inverse plus 10 inverse equals inverse equals. So that gives us 3.3 for that piece there, plus 2 plus 10. So the total resistance, our total, is about 15.3 ohms. From there, you can figure out the current. So the current on the source is 100 divided by 15.3, which gives us about 6.522 amps. Divided by 100 equals inverse equals, there you go, 6.522 amps. At this point, it's helpful to redraw the circuit. We could simplify it to this. We could say this is 6.52 amps. This is our R3 with 5 ohms. And this is our R4 with 10 ohms. And from there, we can easily use the current divider. And just so you can see it, what we've done is we've redrawn this piece right here. So there's the current meter, which is represented by this current source here. And there's R3 and R4 in parallel. To use the current divider rule, we would say the current of interest is the total parallel piece over the resistor of interest multiplied by the source current. The parallel piece is these two, and I believe we already established that as 3.3 ohms. So we would say the current on R4, that is what we were looking for, right? Yep, this current right here. The current on R4 is equal to 3.3 over 10 multiplied by 6.52. So times 3.3 divided by 10, which gives us a current on R4 of 2.17 amps. And done. Just a real quick thing I want you to notice here. This piece right here, this gets people all the time. So this is our total of the parallel piece. Okay, it's of the parallel piece. It is not the same as our total for the entire circuit. It's the total resistance of the parallel piece that you want. Again, that's a trap. Lots of people fall into that. Well, that was one thing we wanted to learn, so that's done. Now we can move on to mesh. We'll start with a circuit that's neither parallel nor series. I believe we've talked about this before, where we start in the lower left corner and we take a walk around the circuit, where we take a walk on a closed loop. And if we do that, we can make a statement. We can say that -5, because we're walking in on the negative terminal of this power supply, plus the voltage on R1 plus the voltage on R2 is equal to 0. And you'll recognize that as Kirchhoff's voltage law, where the summation of the voltages on a closed loop is equal to 0. Okay, and again, all we did was we walked this loop. Another way of saying that is that we have a current A that's flowing in this loop. That takes care of part of the circuit, but now we're interested in the other part. And we could establish that there is a current B flowing in this part. Using the same method, we could start in this corner, and now we can make a loop around the circuit. So we can end up with another equation. So let's see what that looks like. You have a voltage on R2 minus 2 plus the voltage on R3 plus 7 is equal to 0. At this point, we're going to do a substitution for all these voltages across the resistors. You remember Ohm's law tells us that a voltage is the same as a current times a resistance. Knowing that, we can do a substitution for this value. We would say -5 plus 2 current A. And I'm a little lazy, so instead of writing current A, I'm just going to write this as 2A plus 4A. But now we have a problem. Do you see it? We have a big problem here. We have this current in this direction and this current in that direction. They're running at cross purposes to each other. And we have to account for that. So what you would do for this voltage here is you would say 4 times current A minus 4B is equal to 0. And if we were to rearrange that equation, it would be 6A minus 4B is equal to 5. Okay, so hold that thought there. Now we'll go to the second equation and do the same thing. So the voltage on R2 in this case is 4B minus 4A. So again, we have to account for the fact that these currents are flowing in opposite directions, right? A is down and B is up. So 4B minus 4A minus 2 plus 4B. That's this piece here. There is no current A associated with that, so we can just write 4B plus 7 equals 0. If we simplify, we end up with -4A plus 8B is equal to -7. At this point, you'll see you have two equations with two unknowns, the unknowns being what is current A and what is current B. We can use our calculator to solve this. Here's what you would do. First, you would put the numbers into matrix form. Once that's done, you can go to your calculator, turn it on, go to mode, and you want equation, which is 5. And you'll want this one, number 1. So 2 equations, 2 unknowns. Then you enter the numbers. 6 equals -4 equals 5 equals -4 equals 8 equals -7 equals. Then you push equals. The first number there is your current A, which is equal to 375 milliamps. Hit equals again. This is your current B. So current B is negative 688 milliamps. That negative number, by the way, that negative number implies that the current isn't actually going in the direction that you assumed it is. The actual current is going counterclockwise in this case. But that's okay. We just be aware of that as we move on. Now that you have your two currents, we can do something interesting, and we can go back and we can find the voltage drop across R2. And here's how that goes. We have a 4 ohm resistor. We established that current A was flowing in that direction with 375 milliamps. And we established that current B was flowing in that direction with 688 negative milliamps. We should redo this here. So we can say there's 375 milliamps flowing in that direction. And there's 688 milliamps flowing in that direction, which means the currents are aiding each other. Redraw this again. We have, let's see, mode normal, 375 plus 688. So we could say there is 1.06 amps in that direction across a 4 ohm resistor. Using Ohm's law, we can calculate the voltage. So voltage is equal to 1.06 by 4. So our voltage is 1.06 times 4. So our voltage is 4.2 volts. While we're here, let's work another example. To get us started, we'll make a loop. We'll call this current A. We start in the lower left-hand corner, and we walk the circuit. We would record this as 4A minus 10, because we're walking into the negative terminal of supply, plus 6A minus 5, that brings us to here, plus 2A minus 2B, because we have to account for that second current. All of that's equal to 0. We establish the second loop, call that current B, and we will walk around the loop. We would say 2B minus 2A plus 5, because now we're entering on the positive terminal, plus 3B plus 3 is equal to 0. If this was a quiz or an exam and I'd asked you to set up but not solve or simplify, this is where you would stop, right? Everything is there. All the equations are set up. From this point forward, it's just math. But since we're here, let's do that math. So we have A, and A. So what is that? That's 12A. We have minus 2B is equal to, not 10, how about is equal to 15? Because we have that piece and that piece. So there's one equation. The other equation is minus 2A. Takes care of that. How many B's do we have? Looks like we have 5 B's. And that is equal to negative 8. We put this into matrix form. So 12, negative 2, 15, and negative 2, 5, negative 8. From there, we go to our calculator, setup, equation, 2 equations, 2 unknowns, that's number 1. Then you enter the numbers. 12 equals negative 2 equals 15 equals negative 2, 5, negative 8. That tells us that the current A is 1.05 amps and current B is equal to, let's see, what do we get? negative 1.18 amps. As we work these problems, I would encourage you to be consistent with them. Always make your loops in a clockwise direction and always start in the lower left-hand corner. That was mesh. And now we can move on to our introduction to AC. From the previous lectures, the RMS voltage is equal to the peak voltage over root 2. And I believe we established an equation like this. For example, if you had 650 cosine of 377t plus, let's make that minus 120 degrees, what would that look like? Well, this is a volt peak. 377, we said omega is equal to 2 pi f. So in this case, omega is equal to 377. And this here is a phase shift. And it's a delay. The RMS voltage is equal to 650 over root 2. Mode normal, 650 divided by square root of 2. So that gives us an RMS voltage of 460 volts. And we said omega is equal to 377. So 377 is equal to 2 pi f. Solving for f, 377 divided by 2 divided by pi gives us 60 hertz. We also know that frequency is equal to 1 over the period. In this case, that's 1 over 60. So 60 inverse gives us 16.7 milliseconds. And with that, we have enough to sketch this waveform. Now, was it sine or cosine? Looks like it was cosine. Okay. It would look something like this. Where our V max is 650 volts, our V min is negative 650. By the way, this is time and this is voltage. However, that's not exactly the waveform we wanted because our waveform had a phase shift of 120 degrees. And it's 120 degrees late. Let's see if we can figure that out. This point right here is 90 degrees. And this point is 180 degrees. So 120 degrees must occur about here. So our waveform would start with a peak there. So this right here is our waveform of interest. And we would describe that as 460 volts RMS with a phase angle of negative 120 degrees because it occurs late. It's a delayed waveform. If we were to plot that in vector form, where this is the real axis and this is the imaginary axis, it would be a vector like so. This angle would be negative 120 degrees. And the length of this vector would be 460 volts RMS. I think you would agree that this phasor representation is a lot simpler than this time domain representation. Much less to draw. While we're here, why don't we talk about three-phase? Suppose I had a vector there, which I've already drawn in, that's the green one, and it had a phase angle of 0 and a length of 460 volts AC. And now let's add one more vector. Let's put it right here, and we'll set that to 120 degrees, again with a length of 460. and that's volts RMS. We can try to sketch that in on our original drawing. So here we have the third phase. We have phase A, phase B, and phase C in a three-phase system. At this point, I think you'll agree that this phasor representation is much, much easier to use. Let's talk some more about three-phase. If you were to look at a typical building, you would see phase A, phase B, and phase C. You would also see a couple of additional wires. One of them would be the neutral wire, and the other would be the safety ground. So when we get to lab, you'll see this. We have what's called a 5-wire three-phase system. Suppose you had a motor. The first thing you want to do is to make sure that you have a safety ground attached to that motor. So all the metal, all the exposed metal would be grounded. You would connect to phase A, phase B, and phase C, like so. Okay, and this is now a three-phase motor. I should have mentioned that this is a 208 5-wire system. This is the system we'll be using in the lab. Something you might find interesting is that this can directly power 120 volt loads. So let this be the hot wire. Let this be the neutral wire. And then with any AC plug, you also have that third lug. So we'll let that be here. And this would be a 120 volt AC load. At this point, you might be asking, how did you get from 120 to 208? Let me show you. It goes something like this. Let's assume we have 3 resistors connected up like so. Let this be phase A, phase B, phase C, and let this here in the middle be neutral. We'll call that the star. This is an example of a Y connection because it kind of looks like a Y. Granted, it's upside down with these being the parts of the Y. If you were to measure across any individual leg, you would see 120 volts. If you were to measure from any phase to phase, you would read 208 volts, and that's RMS. You kind of see that here because for the motor, we went phase to phase to phase, whereas with this outlet, it was only phase to neutral. Okay, so phase to phase would be 208, and phase to neutral would be 120, which is exactly what we see here, 120, 208. The other type of connection is the delta connection. You would connect your resistors up like this, and then bring in your phases, phase A, phase B, and phase C. One more time, this is a Y connection. It has a center point that goes to neutral, and this is a delta connection. You'll notice it has no central point. That's one easy way to tell them apart. A question you might have is, why do we bother with three-phase? And I would counter that with a motor example. So let's look at a single-phase motor and the equivalent three-phase motor. We'll assume that each motor is 10 horsepower. The single-phase motor costs about $2,600, whereas the three-phase motor costs about $2,100. The single-phase motor weighs about 170 pounds, whereas a three-phase motor weighs about 120. The single-phase motor has an efficiency of about 82%, whereas a three-phase motor is approaching 90%. We see that in every case, the three-phase system is superior. superior in terms of cost and weight and efficiency. If that's true for motors, it's going to be true for generators. It's also going to be true for the transformers and distribution lines that we depend on. Very simply stated, three-phase systems are more efficient in terms of materials, in terms of money, and in terms of the amount of energy they used when compared to single-phase systems. One sidebar before I forget. You see this number 208? If you see a number all by itself, and if you just walk into a control room and you see the number 208, or if you see the number 480 or 4160, and that number is all by itself, you would be safe in assuming that that is volts RMS, and it's measured from line to line, which is what we did down here, where we said that it was 120 volts line to neutral, but it was 208 measured line to line. Here's an equation you should remember. The voltage phase to phase is equal to root 3 voltage phase to neutral. Again, that's phase to phase or line to line, however you want to look at it. And this is line to neutral. In our previous example, we said 208 is equal to root 3 by 120. You can check that on your calculator as 120 times the square root of 3. There it is. There's the 208. Okay, so add that to your note card as well. All right, enough about three-phase. Let's go back and look at capacitors and inductors. The inductor has a coil of wire on an iron core. Remember, the capacitor is two metal plates separated by a dielectric, and that dielectric is an insulator. So we'll see that charges build up on the plates of those capacitors, but those charges cannot recombine because the dielectric is insulator. What we just described is an energy storage mechanism via electrostatic, whereas in the inductor, a current flowing in the wire establishes a magnetic flux, and that is an electromagnetic storage. We can put some metrics to this. In the capacitor, the energy is a function of the voltage squared multiplied by the capacitance. In the inductor, the energy is a function of the current squared by the inductance. I believe we talked about capacitive reactance. That is equal to 1 over 2 pi fc. And inductive reactance, XL, is 2 pi fl. I believe we talked about impedance. The impedance of a capacitor is negative jxc, and the impedance of an inductor, ZL, is equal to jxl. Another way to think about this is to look at the real and imaginary plane. Resistors live here on the real axis. Inductors are imaginary and positive, and capacitors are imaginary and negative. If we look at this, we see this J, which is the imaginary component. Negative J is to point straight down, whereas J is to point straight up on the imaginary axis. Another way of saying that is that this is the capacitive reactance at a phase angle of negative 90 degrees, and this is an inductive reactance at a phase angle of 90 degrees. With that said, we are going to shift to a closely related topic, and that is Eli the Iceman. For an inductive circuit, if we consider the real and imaginary, and if we let the voltage be here, so if this is volts RMS, we would say that the voltage leads the current. So if that's the voltage, we'll let the current vector be here. Voltage leads current. So here we can see the voltage is behind when we consider that the phasors rotate in a counterclockwise direction. If you were a stationary observer here, you would see the voltage waveform first, then sometime later you would see the current waveform. If it was a capacitive circuit, again you have the real axis, you have the imaginary axis. If we let this be the voltage vector, so that's volts RMS, the current vector would be somewhere over here. In this case, it leads by some degrees. Again, as the stationary observer here, you would first see the current vector, and then sometime later you would see the voltage vector. If we were to sketch that in the time domain, if this was your voltage vector, your current vector would be leading. It would occur earlier in time. This is current, and this is voltage. This Eli the Iceman implies that voltage and current are not necessarily going to be in phase, which brings us to yet another very closely related topic, and that is the question of power in AC circuits. Let's focus in on a particular piece of a waveform. So we'll let this be voltage, and we'll let this be a current. There's two lines I want to draw here. So first is that one, and the second one is here. Now we've been told that power is equal to a voltage and a current. Is that right? So power is equal to voltage and current. So if we are in this area right here, we would say, okay, power is equal to voltage and current. Both of them are positive in that piece. If we go to this piece here, something interesting has happened. The power is actually going to take on a different sign, because in this case, the voltage is negative, but the current is positive. Then sometime later, we see that they're both negative. To see what's going on, we need to go back and look at these things. So Eli the Iceman was telling us that there is a phase shift between voltage and current, but he didn't really tell us why. If we go back up a little further, the answer is on this page, because the capacitor stores energy, as does an inductor. And what happens is, as you're on an AC waveform, you must charge that capacitor, then sometime later you must remove the energy from that capacitor. That accounts for the phase shift, and we see that here. Again, where's our capacitor? Right, we see it here. Here's the phase shift. And then if we zoom in on one particular circuit, we see that power does something very interesting here. If it helps, you could think of this as positive power, negative power, and positive power. And during this negative, the energy stored in the capacitor or the inductor is returned. In the case of the capacitor, you had that electrostatic energy. That electrostatic energy is returned back to the power grid. If it was an inductor, that electromagnetic energy that was stored up in the magnetic field is returned back to the power grid. Let's put this into words, see if we can make more sense of it. We would say that inductive and capacitive circuits have reactive power. Reactive power does no useful work. We could say that this power does nothing more than flow back and forth between the generator and the load. This reactive power is described as imaginary because it does no useful work. All it does is flow back and forth between the generator and the load. We have a metric for this known as power factor. We say that the power factor is equal to the cosine of angle theta, where theta is the difference in degrees between our current and voltage waveform. That takes care of most of the lectures, but let's just do another look ahead here. We'll compare DC to AC. We'll start with Ohm's law. We had a wheel that looked like this. It said voltage is equal to the current times the resistance. We have the same thing in AC, and you would read this as the voltage vector is equal to the current vector multiplied by the impedance vector. In DC, we had power. We had a wheel that looks like this, the pi wheel. So power is equal to current times voltage. In the AC world, we describe complex power as the complex conjugate of the current by the voltage vector. We'll come back to this one in another lecture. Speaking of power, in an inductive circuit, we have what's known as a power triangle, where we talk about real power, apparent power, and reactive power. This will make more sense in the next chapter, but for now, just realize this is all a discussion about the phase shifts between current and voltage. If we have an inductive circuit, we have a capacitive circuit. And there, turns out it's negative. Again, with real power here. Angle theta, apparent power. And negative reactive power. We did see some of this in lab. We had an AC source, a voltmeter, an ammeter, a wattmeter, and a load. I can hear some of you now. We never did that. I'm sure you did. We had a small little box, and you plugged your power supply into that. To that power supply, you connected a resistive load. And you made some statements that there was a certain voltage, I think it was 25 volts at 1 amp here. And then you read this box. It told you that you had about 120 volts. There was a certain current. There was a certain voltage. There was volt amps. There was also a power factor and a frequency. You recorded all of that from this little box. Well, that gets back to this. So here you had 120 volts, 60 hertz. You had a certain current, and there was a certain amount of power. When we were all done with that experiment, you drew this picture here, where you had an apparent power, a real power, a reactive power, and you even calculated this angle theta. All of that was due to this power supply. That power supply, which appeared to be a slightly inductive load, causing you to have a difference between apparent power and real power.